Hello class, do you like muffins? I love muffins. So I'm going to show you how to use a simple muffin recipe to understand the stoichiometry of a given chemical reaction. Here is my favorite muffin recipe. 1 cup of water, 2 packs of muffin mix. Follow the directions on the package and I will get 12 muffins. This is like a chemical equation. In fact, this is my muffin equation. Let us say I want to bake 96 muffins for my students. 96 muffins. Now, I can calculate the number of packs of muffin mix I need using this relationship between 2 packs of muffin mix to 12 muffins. Like this. 2 packs of muffin mix over 12 muffins. So muffins to muffins get cancelled. I need 16 packs of muffin mix. This quantitative information, 1 cup of water to 2 packs of muffin mix to 12 muffins, is very important to bake good muffins. Similar quantitative information in a chemical equation is called the stoichiometry of the reaction. In other words, stoichiometry is the quantitative relationship between reactants and products in a given chemical reaction. Just the way we calculate the number of packs of muffin mix needed to bake 96 muffins, we can calculate the amounts of reactants or products in a given chemical reaction using its stoichiometry. Now, let us look at a chemical reaction. This is the chemical equation for combustion of gasoline. Here, gasoline is represented by this octane molecule, which is one of the major components of gasoline. And the stoichiometry of the reaction is given by the coefficients of the equation. So, the stoichiometry of this reaction is 2 moles of gasoline to 25 moles of oxygen to 16 moles of carbon dioxide to 18 moles of water. Now, let us look at the most important stoichiometric ratio in this reaction. That is 2 moles of gasoline to 16 moles of carbon dioxide. Why is this stoichiometry important? Because we know carbon dioxide is a greenhouse gas that is responsible for global warming. We can calculate the amount of carbon dioxide released to the atmosphere due to combustion of gasoline if we know the amounts of gasoline. Of course, we know the amounts of gasoline we use. Now let us use this information to answer a question. I want to find out the amount of carbon dioxide in grams released to the atmosphere by burning 1000 grams of gasoline. Let us label gasoline or octane as gas for simplicity. And we can break down this problem into several steps. That is, if I know the moles of gas, I can find out the moles of carbon dioxide by using the stoichiometry of the reaction. Just the way we calculate the number of packs of muffin mix needed to bake 96 muffins. So the conversion factor here is 16 moles of carbon dioxide over 2 moles of gas. The next step is easy. That is to convert the moles of carbon dioxide to grams of carbon dioxide. I can simply use the molar mass of carbon dioxide, that is 44 grams of carbon dioxide over 1 mole as the conversion factor. Now, the problem is we don't know the number of moles of gas used, but we know the mass of gas that's been used. We can simply use the mass of gas, that is grams of gas, and convert gram of gas to moles of gas. In order to do this conversion, we need the molar mass of gas, that is, say, 114 grams per mole. Now here, The conversion is from grams of gas to moles of gas. So the conversion factor ought to be 1 mole of gas over 114 grams of gas. Okay? Now we have a good plan. So let us calculate the answer. We begin with the grams of gas and convert that to moles of gas. If the conversion factor is correct, grams of gas to grams of gas should cancel. Similarly, we can continue the rest of the calculation. So you see, moles of gas to moles of gas get cancelled. Moles of carbon dioxide to moles of carbon dioxide get cancelled. So the answer is 3.1 times 10 to the power of 3 grams of carbon dioxide. That is 3.1 kilograms of carbon dioxide will be released if we burn 1000 grams of gasoline or 1 kilograms of gasoline. That is slightly less than half a gallon of gasoline.